and Apache Flink. He will be presenting a topic titled Unifying Streaming and Message Queue with Apache Kafka. Unfortunately, there is no AI that figures out that you're in a conference that will automatically silence your phones. So I request please silence your phones yourself. And there will be a 10 minutes Q&A towards the end of the session. I request that you stay back until the Q&A completes, because when people start moving and the questions are asked, it's difficult for the presenter to provide the answers, and it's also getting recorded, so we wanted the Q&A also recorded clearly. Stay back when the questions are, as I mentioned. Please join me in welcoming Mingmin.
All right, thanks everyone for joining today. As introduced, my name is Mingmin. I'm a software engineer with streaming data team. Actually, I'm managing platform team, which is a sub-team within streaming data team. So I'm really honored today to share some of the unique technology that we built at Uber in this particular area. So my team is actually building like a streaming data infrastructure and messaging queuing system on top of Apache Kafka and Flink. So as some of you guys may not know about Uber, Uber is a ride-sharing, food delivery, and transportation network company. Just in case you guys don't know. All right, so here is the agenda today. So first, I'm going to share some of the use cases and the scale of the system that we built at Uber. And then I'm going to talk about some of the motivations of why we are building some of the unique feature sets on top of the open source technologies. And then I'm going to go over some of the high-level design. And at the end, I'm going to I'm going to talk about future work, and then leave some minutes for Q&A. All right, so first, let's talk about use cases and scale.
Can you louder? People at the back are saying they can barely hear you.
Okay, cool. Can you guys hear me? Yeah. Cool, all right. So as you guys can imagine, Uber is moving people and things in real time. So under the hood, we have many use cases that need to be moved data around different stack in real time. So that's how my team is playing in this particular role. So there are some of the use cases that need like this messaging queue solutions, including like rider driver matching, fraud detection, also like push notifications, like when you order a Uber ride, you get like some of the push notifications and text messages saying the driver is approaching, and then a few minutes, the driver will arriving in a few minutes. Right. So that's one of the first use cases for the system that we're building. Right. So Kafka is playing as like transporting those demand supply data and then showing those information on top of the rider and driver app. And under the hood, there is actually a streaming processing system that was actually processing those demand supply data, and then also leveraging pusher services to show those data to the end user's app. It will show like this rider driver app match ETAs, those data on your app. All right. So second use case is for Uber Eats. How many of you know Uber Eats? All right, I would say like 80% or more. It's actually a very cool app that you can order like food from nearby restaurants. So one of the use cases Uber Eats is using, like the system that we are building is, we are actually providing a mechanism for them for Eats app to calculate those ETA data and then show up on the Eats app. And there are a bunch of more other use cases that are leveraging message queuing system for detection, as I mentioned before. Also, you can share your ETA with your friends or family. Sign up, like when a new driver or rider sign up, those data will go to the message queue and then will be further processed by underlying system. And there are a bunch of more other use cases. So in general, just to summarize, we have 5 categories of use cases. So the first one is general pub/sub, publish subscribe use cases, or messaging queuing use cases that is being used by different microservices that are built by other engineering teams within Uber. Second use case is streaming processing. So Athena X that I listed here is actually a open source self-servicing platform that we built from Uber, and it was open source to the community. And it's actually a self-servicing streaming processing system that people can specify like a query, and it will transform those to a streaming processing job, and then run those jobs, and then continues to deliver data to the end application. The third use case is database changelog transportation. So at Uber, we have different kind of database system that we're using. Schemaless is an in-house sharded MySQL database that we built. And we are also using Cassandra and MySQL for different use cases. And then in this use case, it was actually leveraging Kafka to deliver the database changelogs to downstream systems. For example, like money system, fraud detection, they are also keep track of those, any of the database changes, and then do further processing and do their own thing. The fourth use case is ingestion. We are also, some of the data that need to be ingested to the big data lake, and then to long-term storage, including like S3. They are also publishing data to Kafka. And then there are downstream systems to ingest those data and put the data in Hadoop Data Lake and S3. Last but not least, application logging is also leveraging Kafka to deliver those logs to Elasticsearch, Logstash, Kibana for engineers to debug their applications. Yes?
Is Athena X the same thing as AWS Athena?
It's different. It's different. So this is just like, I think it's so different. Like this one is for streaming processing. All right, so here is what data infra stack looks like at Uber. So on the left-hand side, those are all data producers. We have different kind of apps, API services. They are all producing data to the message queue, to Kafka. And then database, those applications also write data to database for persistent purposes. And then database changelog will be also transported to Kafka, to some other system via Kafka. So, and then on the right-hand side, as you can see, there are many different applications and use cases that are ingesting data, including some of the internal services. They are just setting up consumer applications and then consume data directly from Kafka. Flink is a popular open source streaming processing system, and we are leveraging Flink a lot in many different use cases for further process those data and show the data on the mobile app, and then people can do like other analytics for data scientists, and they can build a dashboard on top of that. All right. And then we we also have some of the OLAP database. Pinot is actually an open source OLAP database from LinkedIn, and then Uber is using it for all use cases, including like Eats restaurant dashboard that was actually using Pinot. RSDB is an in-house built technology that was running on GPU, and it's actually leveraging the parallel compute power from GPU, and that was actually one of very popular project that we open source from Uber. And Elasticsearch, Logstash, Kibana was being used for application logging. And ingestion, we have in-house technology which is called Mulberry, which is also open source, to ingest data to Hadoop Data Lake, S3. And then under that, there are Presto, Hive, Spark. People, engineering can use those to do their own applications of machine learning, analytics, ETL, many other stuff. All right. So in terms of scale, the system that we operate are actually running like tens of trillions of messages per day, which accounts for like tens of petabytes of data in terms of data volume. And we are actually we have tens of thousands of topics. And all of those numbers are excluding replications. All right, so second, I'm going to talk a little bit about some of the motivations that why we are building some of the unique messaging queuing features on top of Apache Kafka. So there are two types of messaging. The first one is streaming. Streaming basically means like the messages are like real-time flowing, and then the messages are treated as ordered, and the way that applications are consuming those messages, they are exclusive to other different applications. And usually those data are partitioned into different shards, and sometimes some of the partition will, like the message itself may have a key, and key will decide like which partition those data goes to. And for this streaming use case, the way that how consumer keep track of the progress is via a commit up to, meaning like we keep track of offset within certain partitions or where the consuming up to a certain point. The second category of messaging is message queue. For message queue, usually the messages are unordered, and then those messages are being shared among different applications. And then for those applications, they will act and nack messages based on whether they want to redeliver those messages or not. Think of this category, think about like RabbitMQ, ActiveMQ, those like traditional MQ technologies. So back to Kafka. So how Kafka manages consumer checkpoint? The acknowledgement model is basically the commit up to, as I mentioned, for the streaming category. And then what it basically keeps track of is for each partition, we have like an offset to keep track of like what this consumer application has consumed up to. And why is commit up to not sufficient for some of other use cases for message queue use case? For example, we have some of these two use cases that I'm going to talk about. Post-trip processing. Some of the trip, like the Uber trip, when it's finished, those trip data will be published to Kafka. And then we have a downstream system which will consume those data and then do further processing. For example, like when after your trip, you will receive like a receipt of how much amount, like how much time is for your trip, distance, the start and end point, the dollar amount that is. Those are all like post-trip processing services. And they, for this particular use cases, they need to consume the trip data and then do further processing. And in some scenario, some of the downstream system, they are not ready to process those messages, and they need to nack those messages. And in the Kafka commit up-to model, it doesn't work. It means you are blocking on a particular point. You cannot process other trip data. The second use case is email and push notification. It's similar to post-trip processing, but it's more of like either a driver sign up, when you book a trip, those data will be pushed to Kafka queue, and then the downstream system will use those trip data to send notifications to the end user. And similarly, commit up to it doesn't work because maybe the application cannot process those messages, and they don't want to commit for those particular message. So what they need in this particular case is we need to provide a similar like nack mechanism for those downstream systems to process, and then it should not be blocking for the processing. All right. And why do we build those features on top of Kafka? There are definitely other options. Some people already built KMQ on top of Kafka to provide similar functionality. And you can also leverage some other like traditional MQ technology, like RabbitMQ, ActiveMQ. Apache Pulsar is another like open source project that is already sort of providing the features that we need. And that option is built yet another like message queuing from ground up, which and then we don't choose any of these options. We are building those features on top of Kafka because of a few reasons that I listed here. The first one is reliability. I think Kafka is widely used, and it's already a industry standard that is proven to be very reliable, and we are already using it in many other use cases. So we don't want to we trust and we rely on Kafka for reliability. And of course, it's also known for very good performance. And last one is cost efficiency. We don't want to maintain multiple systems to which are similar but providing like slightly different like feature sets. It will increase the operational and engineering effort to maintain yet another system. All right, so some of the requirements for the things that we want to build on top of Kafka. We want to provide nack feature for the consumption. We want to provide redelivery for the nack messages because they want to reprocess those messages in a later time. Some of the applications they need some kind of delay between those retries. They don't want to retry immediately because maybe the downstream dependencies is not ready to process those messages. And then we also need to provide a dead queue for those messages with all the retries that they still cannot be processed. We need to dump those messages into a specific queue, dead queue. And for dead queue, we need to provide some of the operations for engineers to purge or merge. And they need to be able to inspect those messages and decide whether to dump those messages or redeliver and merge back to the original processing queue. And last two requirements, we are running those systems across on different data center, and we need to provide cross data center failover functionalities, like when the application is failed over to the RDC, we need to be able to provide a mechanism for them to resume from previous processing checkpoint. And last but not least, Uber engineering is using like many programming languages, so we need to provide those features in Golang, Java, Python, and many. We need to provide those clients for those use cases. All right, so how do we provide act nack? So let's take one simple example. Suppose this topic has just one partition, and then on top of like the native Kafka, it provides the commit up to. So what we can do on the consumer application or process is we spin up multiple workers that they can process those messages in parallel. And since those workers or like threads are processing a message in parallel, we need to keep track of what messages already processed, what is completed, what is act, or what is nack. So we actually keep track of those in a in-memory offset checker. And then, so for those workers, we are keeping track of like 2 pointers for one process, one application. One is commit up to, and then the other one is what it has been read. And for each of the messages, we keep track of a timer. And once a message is being act, those messages will be marked as act in the in-flight offset checker. And then continue, in this case, offset 4 and 5 are being act, and 3 is not act, 6, 7, and 8 are not being act. Now, message 3 is being nacked. In this case, what we do is we will reproduce this message 3 back to a separate topic, which is the retry topic. And in this case, we can safely commit the offset back to the original queue. That's step number 4. And then number 5, application is also reconsuming those messages back from the retry queue. People can specify delay in this case, like how much time you want to delay for the retries, and then up to the max retries that was being specified. Those messages, if they are still being nack or the processing is timeout, then the messages will be reproduced back to a dead queue, DLQ, for each. Actually, this is each of this retry and dialogue queue topic will be created for topic consumer group pair. And when people inspect the messages in the dialogue queue, they know those are mal-formatted messages or bad messages, in which case they can simply purge those messages. Or if they know like these messages are good, and they want to reprocess those messages, in which case we provide an operation for them to merge. In this case, the message will go back to the retry queue and will be reconsumed back to the application. All right. So up until now, we have fulfilled like the first 5 requirements, and then the last 2 requirements, cross data center failover and different language support. So how do we do cross replication for Kafka setup at Uber? So we have our in-house replication pipeline, which we call it U-replicator. And U-replicator will basically consume messages from the original Kafka classes and then it will be produce those messages to aggregate Kafka. And we also keep track of the offset mapping when we replicate the data from one cluster to the other. And that mapping will be used when we do failover. So in this particular case, consumer application is running active in one DC, in DC1. And the same application is actually also running in the other DC, but it's passive, which means it's just a standby and it's not consuming any messages from the message queue. And the consumer application on DC1 will process those messages and commit offsets. When the failover happens, the other DC, the application will become active, and the original DC will become passive. In which case, when the failover happens, we have a service which is offset sync service, which are continuously pushing those checkpoints to the other aggregate Kafka queue. In this case, the offset that was committed in DC1 is actually already preserved in the other DC. When failover happens, the consumer application was actually resuming from a safe checkpoint that will reduce the number of duplicates that are already processed from DC1. Right. So we have fulfilled cross DC failover. Last one is different language support. So what we do on the client side is we make it as a very simple API that people just need to specify a message handler API. So in this case, what we do is when they spin up, run this consumer application, we are actually, the consumer itself was hidden from the application, and we are actually using the handler API they provide to process those messages. And based on the return value from the handler, we will do nack. All right, cool. So yeah, so some of the future work. Of course, we are building a bunch of unique and nice features on top of open source technology. We want to open source those things to the community. And we are also building a consumer dispatch proxy that people just need to specify, register a endpoint, and we run those applications for them, and then just dispatch messages to the RPC endpoint. Cool. Some of the links, we have some blog regarding some of the things that I just talked about, and some of the replicator that I just talked about in the previous slide. And we also have a bunch of other open source projects that can be found in eng.uber.com. Feel free to explore some of the the unique and interesting project that we built from Uber. All right. Yes. Cool. With that, I'm open to questions.
Okay, so I see obviously Kafka, right? And
yep.
Not just Kafka, but I see a bunch of different clustered applications, on the right of your, one of your intro pictures, right?
Okay.
Hadoop and then Twing and all those, so a bunch of those things here. So, how do you guys kind of manage or orchestrate all of these applications? Do you guys do each of those kind of, in a sense, quote unquote, manually, individually, or do you have some sort of orchestration technology like Kubernetes or things like that? Do you guys containerize these applications and Kafka in particular?
Yeah. Actually, at Uber, we have our own in-house orchestration framework for either stateless services, which is you monitor, you deploy, and we also have orchestration framework for stateful services for Kafka itself and storage. They are I'm not sure if it's already open source or not, but it's similar to Kubernetes in the concept, but it's actually an in-house technology that we built. Not my team, but like some other team within Uber built.
Yeah. So second question. So lots of data going via Kafka. So any comment in terms of schema, right?
Yeah. So the question is about schema management with Kafka. So actually, we have a few. Actually, there's one schema service that the ingestion team build and maintain. They are building on top of Avro, and for the data that need to go to Hadoop data lake, it's enforced to use the schema on top of Avro, such that the Hive table Presto query, they can leverage the schema that was already defined, and the schema itself can be can be extended. Like when you add a new field, that will not break some of the old data or like the queries that you already have. So that was kind of like a standard thing that engineering teams should be using for data that goes to the big data. But for microservices, it's usually up to the application owner to define the schema. Either in the old days, people use Thrift. Nowadays, I think it's more of a standard for people to use protobuf to define for those internal services. And then for logging, for Elasticsearch, Logstash, and Kibana, the data is usually in JSON format. So it's not really free format, but like it doesn't enforce the schema in this particular case. So I would say it's a case by case, but you can think of it like there are like 2 or 3 like schema management things that are enforced for different use cases.
You have messages larger than 1 megabyte. How do you handle that?
Okay, so the question is, do we have messages larger than 1 megabytes? So I think 1 megabyte is sort of a standard. Like we don't want to exceed, for performance consideration and then operation. And we do have some use cases that may exceed more than 1 megabytes, and we whitelist those topics just to make sure like they, if they need to have more than 1 megabyte messages, or we still put like 10 megabyte upper bound in this case. But in case they need to use these large messages, we need to put it in a special setting to make sure it doesn't break and degrade the performance of the cluster.
What were the reasons behind building your own replication system versus using the out-of-box tools like Kafka for cross data center replication?
So when we that actually goes back to the history of how Kafka is being used at Uber. So we start use Kafka in early 2015, and at that time I think when we first start using it, we are using open source Mirror Maker to replicate data across data center, but Mirror Maker itself has many problems that we run into. And for example, I think some of the issues that we run into, including like when we expand a topic to more partitions, the mirror maker suddenly dropped like all of the traffic, and then it has a big spike. So we run into multiple of those operation headaches. So we instead I think we just built things. We just modify the open source mirror maker, and then actually until now it's totally different from open source mirror maker, and that is actually originated from mirror maker. You will be getting. And Kafka Connect itself, when we build this technology, Kafka Connect is, I guess, is not there yet, and we are not motivated to switch. And I think itself is provided by Kafka Connect is provided by Confluent, and I think it's not free. So since we already have the technology that we built in house, we don't want to and it's working very well. So we are not we do like keep an eye on those new technologies, but we are not motivated to switch or change in any immediate term. Yes.
And thank you for your interesting talk. Just a quick question. What do you guys do? I mean, in terms of like nack architecture, and if the client dies completely, like for a long run, like how would you like keep the messages that you're supposed to deliver, but the client isn't there anymore?
Okay. So the question is, in case consumer application dies, how do we manage those in-flight messages, right? So we do keep track of like this one, commit up-to, and when the consumer application crashes, this one actually doesn't move, right? So the checkpoint that we have on Kafka side is what is there is already there. Like what is already consumed means it's already being act or being redelivered to the retry queue. Means it's safe for the commit. And when it dies, it will not continue deliver those messages. And the message is actually persists in either in original queue or in the retry queue. So it's safe in this. Do I answer your question?
Yeah, just when clients, for example, get back, you just deliver all the messages, for example? For example,
yeah.
Your phone dies.
Okay, I see. So I guess your question is, what if consumer application just nack every single message? I see. So in this case, we do have like some kind of quota that we set on top of like both original topic and the retry topic. And when it nacks all the messages, it means like your retry queue will blow up, right? And since we set up the quota on the Kafka side, so it will basically slowing down the application, the consumer application. And what ends up happening is, in case the consumer application crash, has this issue, then all the messages will be end up in a DLQ. And usually we will set up like a monitoring of like how large this queue should be. And in case it exceeds certain like threshold, we already know, like the application owner should know about this, and they should be debugging if there's any issue with the consumer application. Yes.
We have one last question.
Okay.
Running out of time.
Okay, so my question is, you're getting trillions of messages per day, so will the storage of the into the database become a bottleneck to you? And then also, how are you treating the duplicate message using Kafka?
All right, so the first question is trillions of messages per day, does it explode the database? So if you look at the Kafka here, it's actually leveraged as like a queue, and it's not storing all the data.
You're storing in Cassandra.
Here?
Yes.
Oh, okay. So not all the data is going to Cassandra.
Okay, but still, like, I'm not sure how it's the traffic, but we are facing a bottleneck. We're having the same design on this application in our company, but we identified that NoSQL database are having becoming a bottleneck. So I'm not sure when you publish to Kafka, you store
Right.
database first and then publish. That's my assumption, but that is causing a bottleneck. So I'm not sure if you guys have the same bottlenecks too, and how you resolve it. And yeah, and my second question is about handling the duplication.
Okay, sure. So for your first question, the database, does it become a bottleneck? We don't produce, or we don't log all those data to database, only the critical data. For example, trip data is definitely super critical. Payment data is, of course, very critical. Not all those data. The data here that I'm talking about is data going to Kafka. It's not data going to database. Database has small scale compared to data volume for Kafka. Right? So, and then we are also building a sharded MySQL database, which is called a schemaless, and that is supposed to be more scalable because it is sharded. It's across different data center, and it's not just one instance of MySQL. In this case, it will make it more scalable. And your second question is how do we deal with duplicate data on Kafka? Actually, the solution that my team built doesn't provide the dupe. What we have is we are actually building like a monitoring system to, ingest every single messages and do some kind of windowing for the hash and check if there are some kind of dupe rate. And for business critical topic, we will report those dupe rate to our end users. And most of the time, it doesn't have the dupe rate super low. And then how does end users deal with duplicates? So what they usually do is they will cache the data. And I guess one of the solutions is they cache the data to Redis with some like TTL, and then when they are processing those messages, they will check if those messages is already being processed. And since like duplicate, if it happens, it usually happens like within a very small time window. In this case, it will help dedupe those messages.
Thanks for Mingmin. It was a great presentation. This is
Right.
appreciation from Data Cornell.
All right,
Thank you.
cool, thank you. Okay.
Short class.
Okay.